Hello, everyone. My name is Martin Wallace. I'm presenting in lieu of Kenichi Sugihara today. He's my research supervisor. Um, he's from Gifu Kenzai University in Japan, and this has been his work for 15 years, so I'll try to present it as best I can.
I help you, okay?
Sure, next. All right, so our work is on 3D generation of building models from digitized building footprints used for rapid damage assessment. So you can see here that we have a city model in Esri, and people are, we use the, oh, sorry. Based on the information here with the stories, area, and the roof type, we are able to generate these 3D building models rapidly. So background objective of the research. 3D building models are important information infrastructure. 3D building model, they're time and labor consuming to produce, and technicians are drawing and building polygons manually with digitizers, depending on aerial photography. Not all buildings are orthogonal. So related work, automatic generation by sets of rules such as L systems, fractals, and straight skeleton, created an archaeological site of Pompeii and suburbia model of Beverly Hills at SIGGRAPH 2006. Import data from GIS, classify as basic shapes. They were able to start City Engine with Esri.
Just tell me when you want to go.
Okay,
further,
sure.
Okay.
Sorry, everyone. Next, please. Next. So our process for generating the 3D models, we partition the building footprints into rectangles where there may be a loss of orthogonality and an overlap or gap between rectangles, since not all building polygons are orthogonal. After rectification, orthogonalization of partitioned rectangles, there is no overlap or gap between the rectangles. And we're able to quickly generate a 3D city model like this. So far our workflow is from a GIS application, we're able to quickly digitize the building polygons, giving them different roof attributes such as stories and area. And then from there we move into a Python and Visual Basic module where the polygons are partitioned into rectangles, and the rectangles are then moved into a CG module where we're able to generate 3D primitives, and based on Boolean operations, we're able to generate 3D houses. So you can see a little bit more of our workflow here and how the houses are able to be generated. So this is a little bit more of how the rectangles are partitioned. So the set of building polygons is partitioned into a main rectangle and then sets of branch roof rectangles, which are then used to generate the roof shapes. So this is a breakdown of how our algorithm works for generating the building models. The building shape is divided into sets of right and left turns based on traversing in a clockwise manner. And then dividing lines are created between the polygons, which are then divided into main and separate branch roofs and partitioned based on the number of vertices. Next. So quadrilateral is numbered clockwise with the start point of the longest edge facing right as point 1. During the searching stage, an active quad will search for an adjacent quad by locating which quad the checking point on the active edge contains. The mutual vertex is which the rectification procedure uses a standard position for rectification. The process here of the rectification into 3D or into separate quadrilaterals, and then generated into a 3D building module here from the CG module. So the main point of our work is that we're able to generate several different roof shapes based on the building footprint. You can see here, these are all different roof shapes that we've been able to generate. Leaned roof, gable, temple roof, mansard, gambrel, hipped roof, mixed, oblong, double leaned, and temple roof. So in the CG module, primitives are generated based on the quadrilaterals that have been extracted from the GIS module. Boolean operations are used, making holes in the building, body for doors and windows. The rotated and ridges of the hipped roof, depending on parameters on the slope of the roof. And then placing the parts of the house according to the location of the parts calculated with the GIS module. Texture mapping is then applied to the and copying of the second floor to form the third floor or more in case of buildings higher than 3 stories.